try to prove big O of this thing, you need to provide that particular constant value, because that is how we would solve this thing. Okay, so for proving this thing, let's prove this thing analytically for now. So we have n squared plus 3n plus log n. For this, we can say that this function will always grow slower than this particular coefficient here. Let's multiply all of them with this particular coefficient. So 3n squared plus 3n plus 3 log n for all values n greater than 1. This condition holds, right? Similarly, we can also say that 3n would always grow slower than 3n squared. And 3 log n would definitely always grow slower than 3n squared. So we can say that 3n squared plus 3n squared plus 3n squared for all values n greater than 1, where 1 is n0, we have the upper limit of 9n squared. That basically means that our function is big O of n squared. We can also say that for an n value of n0 value of 10, we can say that for all of these parts of our equation, every part of our equation grows slower or equal to n squared for n squared for 3n, and n squared for log n. So if our bound is n0 equals 10, then we can say that the upper bound is 3n squared. Again, basically means big O of n squared, right? So essentially, this example shows that we can replace this 3n and log of n into n squared just to figure out the maximum possible time that our equation might take given some constant. Similarly, for big omega, we need to find out a constant that is always going to grow smaller than our current equation. So we have 3n squared, we have cn squared here for some value n greater than n0. And we know that n squared plus 3n plus log n will always be larger than n squared, where the constant is 1, where n is greater than 0, right? So for a constant of 1, whenever we add something to n squared, that is 3n plus log n, basically we are adding some positive numbers, right? Because n is always positive. And we can say that this equation has a big omega of n squared because that provides the lower bound. So we have the upper bound, that is big O of n squared. We have the lower bound, that is big omega of n squared. And so now we can say that this equation is within this bound, that is theta of n squared. Yes, Brian, you raised a hand.
Yeah, so how did they find the n0 in these examples?
So basically what you need to do is, so I'm guessing you're asking this particular n greater than 0 or this n0, right?
Correct, and like on the last slide.
Okay, so think about it. So if n was 1, let's take that this was log base 2, right? So if n was 1, this is 1 squared plus 3, that is 4, plus log of 1. Log of 1 is 0, so that basically means 4, right? So we have 4, and then that will always grow larger than n squared, that is 1 squared, that is 1. So you need to figure out a particular n0 value for which this constant, anything times that particular constant, will always grow either slower or larger than your equation. So you need to analytically find out that particular number, or you can always use the limit functions.
So you just plugged in numbers until you found the right one?
Yes, basically yes, that is what it boils down to.
So, so it's a trial and error process, or is there
It's usually a trial and error process, but when you do have an equation for this particular algorithm, you can always analyze it visually and figure out that for what value of n would this be a lower bound, or what value of n would this be upper bound. But in essence, yes, it's a trial and error process. You can also derive it, but if you're going to derive it anyway, why not use the limit function directly to solve it? That's what I'm saying. Where you have provided that we have some limit equations that for big omega it is going to be greater than 0 fn by gn, for big O it is going to be gn by fn greater than 0, and so on. So if you can find out the value of n0 by just doing a derivation, but in essence, if you're doing derivation, why not do a limit? That's what I'm saying. Does that make sense? Because if we derive this particular thing, we know that the minimum is going to be at n = 0, right? Right. So if you're, you can find out the value of n0 by just doing a derivation, but in essence, if you're doing derivation, why not do a limit? That's what I'm saying. Does that make sense? Because if we derive this particular thing, we know that the minimum is going to be at n = 0, right? I hear confused silences.
Yeah, so I guess my question was that like if I am trying to derive it from the equation, even then is it possible to uh, like even then is it a trial and error process that I assume and not, or
Okay. N naught is more or less a trial and error process. I say more or less because, okay, so first let's talk about C. So we know that we can find out C by just figuring out how a function actually grows. We did this here. Let's look at the very first example. We did this here, right? We had 3n squared plus 10n plus 5. We assumed that every coefficient was just 10, and that made it into 10n squared plus 10n plus 10. And we said that every part of this equation grows faster, grows slower or equal to 10n squared, right? So 10n squared plus 10n squared plus 10n squared. That gave us 30n squared, and that gave us a C, right? But we know that since n is basically a number that is any number from 0 to infinity, if we had n equals to 0 in this particular situation, when we say that n equals to 0 for this thing and n equals to 0 for this thing, right? So we know that n equals to 0 will not work, right? Because that would not give me an upper bound, because n equals to 0 basically means this part is 5 and this part is 0. But for any values larger than 1, we see that this bound does work, right? So 3 plus 10 plus 5 gives you 18, and 30 times 1 gives you 30, so that becomes an upper bound. So N0 has to be analyzed and trial and error, as you say, but C can be found out mathematically. But you need to figure out a value of N that is the minimum most value after which your equation grows.
okay,
Okay, makes sense. You see how 0 cannot be N0 here?
yeah.
Okay. Any other questions? You can have any question. You can say, I have no idea what's going on right now. I don't mind. Okay. So let's look at a particular example. Let's say that I'm claiming n plus a to the power raised to the power of b is theta of n to the power of b. That means that there is a constant times n to the power of b, c1 and c2, where c1 times n to the power of b defines the upper bound, c2 times n to the power of b defines the lower bound. Can someone tell me how I would prove this thing? And before you begin, let's take some assumptions that a is going to be, for the upper bound, let's assume that a is going to be smaller than n. For the lower bound, let's assume that a is going to be smaller than n by 2, as at least the absolute value. A can be positive, negative, but let's take the absolute value. Okay, I don't need the answer right now. Tell me, how would I approach to solve this problem? Let's bring my thingy up. Okay, so we have n plus a raised to the power of b, and I'm claiming that it is theta of n to the power of b. For this, I need to show that we have some constant c1, where c1 times n to the power of b will always be smaller than n plus a to the power of b. And c2 times n to the power of b will always be larger than n plus a raised to the power of b.
I guess with the limits.
With the limits, yes, but how? I mean, so let's say that with a limit, I can say n plus a raised to the power of b divided by, let's say n tends to infinity, I have divided by n raised to the power of b, right? But can I extract out n to the power of b from this equation, or any n term here? Otherwise, it is essentially infinity divided by infinity. That does not make sense, right? How do I decompose this particular equation into a smaller set? B could be anything. If b is squared, we have n squared plus a squared plus 2an. If b is 3, we have more equations, right? N cube plus a cube plus 3an, 3a squared n, 3n squared a, blah, 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 and all of those terms. So we are not sure how we can get some amount back from, cut some amount out of this equation, right? We cannot divide this with anything.
Yeah, I mean, yeah, we are not sure how we separate a, n, and a.
In some legitimate term, right? Otherwise, it is just infinity divided by infinity, right? So essentially, what we can think of it is, so we are assuming that we are making two main assumptions. I'll come to these assumptions later, but after this, but essentially we are saying that for upper bounds, our absolute value of a could be positive or negative. Our absolute value of a is going to be less than n. It will always be the dominating number. And for the lower bounds, I'm going to assume that our absolute value of a is going to be less than n by 2. Right? That is just an assumption. I can also solve this equation by not assuming these things where a is greater than n and a is greater than n by 2. But in general, for simplicity's sake, we are going to assume that these things are true. And then because assuming the other things makes it a bit complicated, but also very interesting.
So for the upper bound, can we assume then that n plus a tends to n?
N plus a tends to n. Yes, but we are just saying that it is less than or equal to n. We are not saying anything about that it is much larger. Much smaller. We are not saying that it is much smaller. That would be saying that a is much smaller than n. We are not saying that. A could be anything, but it is less than n. That is what we are assuming. Make sense? Okay. Now, in order to solve this, we need to first figure, okay, we have some answers here. Cannot we expand the binomial equation and divide by n to the power of b, a plus 1 plus a divided by raised to the power of b. In the limit, it will be 1. That is a nice answer for both of you. Yes, we can do that. We will divide both of them by n to the power of b. And since we're dividing by n to the power of b on both cases, that applies to both. Yep, both Yaswanti and Vamsi are correct. But let's, and you guys basically ruined my explanation. Thank you for that. But let's look at another explanation here. Yeah, you guys are correct. And using the limit, we do have the solution for this particular thing. And when we have equals to 1, we can say that it is going to be a big O notation and also a big theta notation as well, right? Okay. Now, let's say that I also want the constants that bound this equation. I want the value of C1 and I want the value of C2. So given any arbitrary equation, that is what we usually require in order to prove that a particular equation is within these bounds of theta. Because remember, for theta, we also, apart from using the limit, yes, Yaswanti and Vamsi, but we also need to show that there is some constants involved here, right? So you guys are correct, but let's look at another approach to solve it.